Hey everybody. Today we're talking about the t-distribution. So, to start with a little bit of motivation. A major problem with confidence intervals for the mean and other inference techniques is the presence of the population standard deviation sigma in the formula that's used to construct them. And in practice, we hardly ever know the population parameter sigma any more than we know the population parameter mu. So, confidence intervals are based on the sampling distribution of the sample mean, x bar, which is always approximately normal with mean mu and standard deviation sigma over the square root of n by the central limit theorem. To say that a little bit differently, any sample mean can be described using a z-score. So you take the value you've got, x bar, minus the value you expected, mu, divided by the standard deviation. And since we're talking about the distribution of x bar, the standard deviation of x bar is sigma divided by the square root of n. In the confidence interval formula, the value z star comes from the fact that x bar minus mu over sigma divided by the square root of n has a standard normal distribution, as I've shown here. So if you don't know sigma, the obvious thing to do is to replace the population standard deviation sigma with the sample standard deviation s. And if you do that, you get the formula x bar minus mu over s divided by the square root of n. Unfortunately, that no longer has a standard normal distribution, and that's why I've labeled it t instead of z. The reason it's not a standard normal distribution anymore is that the denominator now changes with each new sample. So the sampling distribution of this statistic does not have the distribution n of 0, 1. The distribution of this thing, t equals x bar minus mu over s divided by the square root of n, has been studied and documented just as thoroughly as the standard normal distribution has been. So this random variable t is said to have the student t distribution with n minus 1 degrees of freedom, abbreviated t of n minus 1. A lot of times we just call it the t distribution. Now, the t-distribution has a shape that's very similar to the standard normal distribution, just with more spread. And that's more true when n is small. So this picture is typical. The center of any t-distribution is at t equals 0, and it has a generally bell shape. Here, the dotted line is representing the PDF for t of 1, the t-distribution with 1 degree of freedom. The dashed line in the middle is t of 4, and then I've also put the standard normal distribution with a solid line. So again, notice that the smaller the value of t, the more spread there is here. The lower the peak in the middle, the fatter the tails. As t gets larger, the t-distribution gets closer and closer to the standard normal distribution. Since c is a continuous random variable, as usual, we compute probabilities using the cumulative distribution function, or CDF. And this represents the probability of getting a random t-value less than or equal to whatever t-value, little t, you might specify. I've shown the CDF here, the probability that big T is less than or equal to little t. So as usual, you should compute this using technology. Although tables are available in old school textbooks, I strongly recommend against using those. My technology of choice is R, and the command for the CDF of the t-distribution is PT. And you need to specify the value you're interested in, as well as the number of degrees of freedom. So for instance, to get the probability of randomly getting a t-score less than or equal to 1.2 in the distribution t of 11, so 11 degrees of freedom, is pt of 1.2, 11. If you execute that, you get about 0.8723. Using the CDF, we can get the probability that t falls in any particular range that we might be interested in, just as we would using any other continuous distribution. For instance, the probability that t is between negative 0.5 and 0.7 in the t-distribution with 7 degrees of freedom is pt of 0.7, 7 minus pt of negative 0.5, 0.7. Overall, you get 0.4305.